Hi. Look.
Hi. Ooh, what you got there? Did you get a new phone?
Yeah.
Very cool. But wait a minute. Why are you in 3G? This is a 4G capable phone.
4G.
Yeah. Do you have a minute? I could show you some things about 4G. I'm kind of a fan. Okay. Okay, so look how fast the data is in 4G compared to 3G. All right? So check the download, for example. Pretty fast, eh?
Yeah.
Yeah, all right. Now, and let me show you something really interesting. Call me while you're on 3G, okay?
Okay. So?
That took about how long?
5 seconds.
Okay. Check this out. 1 second.
Whoa. Now I really need to think before I make a calls.
All right, well, this is the really cool feature that I wanted to show you. So during a call, that you can actually switch to video if you want, back and forth.
Really?
Yeah. Want to
Can
try
you
that?
show?
Yeah, here.
Whoa, that's impressive. But can you tell me later a little bit more? I have to get my stuff from locker room.
Okay, so, but in that case, take my phone with you.
Okay.
All right, and stay on the call so we can. I can tell you more at the same time.
All right. Good.
Okay.
Yeah. So
all right.
Please tell
off
me
you go.
more.
So, actually, while you're going, listen. Can you hear how crystal clear the voice is in 4G?
Yeah.
And when you compare it, like you can really hear the difference to an HD call. So now I'd like you to check. Have a look at the screen. What network are you using now?
I'm actually using 3G now. So, but I was starting the call into 4G.
Exactly. So you see, the connection doesn't break, even though you've moved from 4G down to 3G or even to 2G. So, okay, now go get your stuff and I'll show you a few more 4G tricks, okay?
All right. Thanks. Bye.
Bye. Wait.
Good evening. My name is Ravi. We are here to discuss about the LTE network architecture and its underlying interfaces and protocols. So before we get into the actual topic, let me give a brief introduction about myself. I'm Ravi and I have 15 years of experience in the telecom industry, majorly in the R&D, of course. But then for the first initial couple of years, I had experience also in the field for one of the popular mobile network operators in India, where I was primarily working on radio access technology. So of late, I also had a good amount of experience in the end-to-end network laboratories in Nokia, Bangalore, wherein my task was to handle majority of the radio network elements and also packet core. So in that perspective, I can say that I have got a good amount of experience when it comes to end-to-end network system handling. And then for the past 2 years, I have been working on architecture and specification team, leading one of the leading products in radio networks. So that is about myself. So let's get started. So here comes the agenda. The agenda for today is overview of 2G or 3G architecture, evolution of LTE architecture from 3G. I would say both 3G and 2G in the context that it'll be helpful for us to understand how both core network and radio network have evolved. I will just try to give a brief introduction about 2G, 3G, and then try to see how the evolution is depicted there. And then before we talk about the details of network elements and the underlying protocols, it is very important for us to understand in the networking world how the open systems interconnect model works, and then how does it inspire or how does it motivate to evolve models like telecom layer models, which are typically used in GSM and WCDMA or LTE networks, what we have today? How do they evolve from the underlying OSI model? And what are the typical aspects of OSI model that we reuse in, let's say, at LTE network architecture? Once we discuss all these aspects, we will try to go to the LTE network architecture where the actual components of LTE network are explained in detail. All this explanation will not be very complete if one is not talking about the LTE network interfaces. So what these interfaces are, what do the protocols they operate on, and what kind of services these interfaces provide uh, to either ends which are connected to each other. So we will try to understand them. And then once we understand, it'll be easy for us to appreciate how the division of networks is done within LTE. Let's say radio network versus packet core, packet core network versus IMS network, and then we also will try to touch base upon a little bit about the CS core network, primarily that kind of a network which is responsible for providing voice-based services in the network. So that is the agenda for today, and so let's move on. Okay, I guess many of you who have had heard about GSM or WCDMA or LTE networks, you must have also heard about something called as 3GPP, right? But I'm not sure to what extent you people are aware that this is the particular organization that is responsible for formulating the services requirements and also responsible for formulating the list of services and list of interfaces, list of protocols, and what kind of technology that vendors and operators and scientists together need to prepare. So 3GPP stands for Third Generation Partnership Project. And to visualize what kind of organization it is very important to understand that any network or let's say any technology does not directly get discovered or invented over a night, right? So you have basic user requirements evolving every day, and when those sort of requirements evolve every day, the kind of technology that is available as on date needs to also continuously evolve, right? So for example, you take this specification, so-called roadmap. It's not a roadmap because the date lines that I mentioned here are already done and they are at the max of 2008 and 9. But then when you see from 2000 towards 2008, you will understand how 3G network, for example, got slowly evolved, how the services got ramped up, how it improved. When I say improved, it improved in terms of meeting the user expectations. And then when the ecosystem developed, how LTE got formally announced in 2008, what we call it as UMTS release 8. So all these technologies which evolve are tagged, are mapped under particular releases. So don't get confused by too many jargons used here. UMTS basically stands for Universal Mobile Telecommunication System, and it basically represents the 3G network. When I say 3G, it is not just one part of the network, it is an end-to-end network. It comprises of both radio network and also it comprises of core network as well. So what is radio network and what is core network? We will see as we move forward. But it is important to understand that when 3G network got evolved, the basic requirement when it evolved was to provide better voice service and better. Can anybody guess what else other than voice in those days? It was already packet service, right? What do I mean by packet service? It's a data service which is available on the phone. And now when feature phones gradually evolved into smartphones, and at the beginning of a smartphone era, what was the basic way in which you could actually use the packet data service of the network? What were the various forms of usage? Can anybody guess? Was it a video call on day one? I don't think so. It was basically opening an internet page on the mobile phone, right? It was opening an email, let's say a Gmail or a Rediff mail or a Yahoo mail, opening some sort of an email box over the internet. That itself was considered to be one of the major data usage pattern on the mobile phones. So when initially 3G got evolved with UMTS release 99 or release 4 architecture, it actually was meant for providing a better voice quality service as well as better packet data service. So when 3G was there, when 2G was there initially, that is GSM, of course, you have had good enough capacity and coverage, but then the problem was in terms of the bandwidth, or let's say the throughput, or let's say the famously known as upload and download speeds, which were available on the mobile phones in those days. So with GSM, you had as much as less, I would say, as around 90 to 100 kbps. With the evolution of GPRS technology, you could afford something around 120 to 150 kbps, and with the advent of uh, let's say a 2.5 or 2.75 technologies as edge, which is enhanced data rates for global evolution. User had the privilege of a download speed of around 400 kbps, which is in itself very advanced in those days. Of course, it doesn't mean that every mobile user used to get it, but then that was the maximum data rate available in those days. So 400 kbps to download a web page, to download an email was itself an achievement in those days. So basically, when uh, WCDMA or let's say UMTS or 3G evolved, the basic requirement was to ensure that each and every user is getting around 2 Mbps, which is around 5 to 6 times of what you are able to achieve already in 2G, and then provide better uh, voice quality. How do we do that? Of course, there is a lot of theory around it. You can obviously refer to Google and get it, but then the basic idea here is you had better codecs and better air interface technologies in 3G compared with 2G. So GSM, you had GPSK modulation, and here you have better modulation techniques in 3G in the form of WCDMA and also better bandwidth. So for a single carrier, I would say a carrier is that which is responsible for carrying your user data or a user voice information. So it is around, I would say, roughly 20 times more in bandwidth when compared with a 2G. So can anybody guess what sort of a bandwidth I'm talking about when I compare 2G and 3G? It was around 200 kilohertz. It's a fixed carrier bandwidth in GSM. What we had in 3G was around 5 megahertz, so around 25 times the carrier bandwidth. So there is obviously a better possibility to have better voice quality, and it's also possible that you'll have good amount of data throughput possible for a single user. So initially when it evolved, that was a major target. Slowly when it evolved and when the smartphones started getting developed, and on top of that, people started realizing that it is not just email as well as web service that we can use in 3G. You have better phones, you have better technology, and you had better technology apps as well. So when apps and phones and network, all this ecosystem starting getting developed, then you had new requirements coming up from the users. So why not why not download better images? Why not download small videos which can be stored on the phone, or rather uploaded from the phone? So when people started realizing the importance of downloading videos, that's where the technology HSDPA, high speed data link packet access, evolved. So it is in the year of 2003 that UMTS had release 5 with the help of 3GPP. Basically, the 3GPP, as you might have understood by now, is a congregation of network operators. It's a collection of network operators. It's a collection of mobile network vendors, or let's say the infrastructure providers like Nokia, Huawei, Ericsson, and ZTE, and so on and so forth. You had so many people initially. Of course, the number has gone down today, but then these are a collection of mobile network vendors. You have service providers, or let's say the operators in the form of, when I say operators, I mean top notch, right? It can be Docomo, it can be T-Mobile, it can be Sprint, it can be AT&T, it can be Uradio in the Middle East. It can be Airtel in India. You had so many advanced mobile network operators and vendors and also scientists from the field of telecom who all gather in a place. They deliberate, they discuss, and they see the existing technology. Is it sustainable or not? Can we provide better technology, and can we provide better services to the user, to the end user? So during those discussions, they come up with new possibilities of providing services to the users, and then they check whether the underlying network elements what we have today, the underlying network architecture what we have today. When I say architecture, it is not just about network elements, it's also about interfaces, and it's also about underlying protocols which are responsible for making those network elements operate in an open environment. So they all come up with this, and then they formulate certain rules, guidelines, and we call them as specifications. So 3GPP comes up with specifications. It was release 99, release 4 specification in 2000. It was release 5, or let's say 2003, in the year of 2003, that they have come up with release 5 specification. And this majorly catered to HSDPA, as I said, high speed data downlink packet access. And then IMS, of course, it's all about providing packet-based voice services. We will see what is that. So it provided IMS, and then when people started using downlink, or let's say the downloads onto the phone, there was also this fancy idea of integrating cameras onto the mobile phones, or content-based usage. When a person records an audio on his mobile phone, there comes a naturally an idea, right, that you can upload these audio or a video on your phone and share with it to your user, or let's say with a friend or with a family member via mobile network. So there came the idea of HSUPA, which catered to the uplink, or in your terminology, upload, high speed uplink packet access. And then you had MBMS, mobile broadcast messaging service. This is basically for broadcasting from the government services to the end user or citizens in a particular area in the event of a calamity, or some sort of a cyclonic uh, broadcasting information that you would like to have. That is possible using MBMS technology. And of course, when cellular network, or let's say the wireless network, or the mobile network got evolved from 2G to 3G, and in 3G you started having advancements towards better technologies. There was also discussion about wireless LAN interworking. So IW stands for interworking, and everybody is aware that, right, even until very recently, that wireless LAN always provided better downlink and uplink speeds, right? Being a cable environment, being a cable driven network, it always provided better throughput, or let's say better speeds in uplink and downlink directions. I mean, upload and download speeds. So there was a discussion, or there was a study done how to integrate this uh, this particular wireless LAN technology with the mobile phone technology, can we do an ideal mode selection, reselection, what we call, or let's say connected mode handovers? You will see what is handover going forward. So there was study done on that, and then you release 6 actually got uh, some some level of work already integrated with this wireless LAN interworking. And then, as I said, when the ecosystem develops, it is not that technology gets developed overnight. Particular technologies and network mobile operators as well as infrastructure vendors, they always anticipate what kind of requirements are going to come. It's not just 1 or 2 years in advance. They always have a vision of at least 3 to 5 years, and then they have a good check of their existing infrastructure whether it is sustainable, and if not, they will always think about better technologies as well. So that is part of this idea that LT studies and MIMS evolution were dealt with in release 7. There were few prototypes, there were few pilotings done, there were few proof of concepts done in 2007 in the form of release 7. And then finally in the year of 2008, when 3GPP released release 8 architecture, it was formally announced that technology called as LTE or 4G will help in providing radically different user services with the help of, I would say, to a major extent, I would say, reutilization of the existing infrastructure, but then better air interface technology in the form of LTE. So, and also you will see what is EPC and what does it stand for. But just remember that in the year 2008 and 9, we had UMTS Release 8, which is responsible for LTE commercial rollout. Okay, so as is given here at the bottom, you can see that LTE has been developed by the same standardization organization. So let's move on. I think you are able to understand how the technology gradually developed. It was basic intention was to have 2 Mbps data link data download speeds here with the help of UMT's release 99, and then slowly developed. I would say with the HSDPA, you were able to achieve around 21 Mbps. And of course, everybody is aware what LTE as a basic minimum service can provide. It can at least provide around 70 to 100 Mbps in LTE network. So that's about the user experience aspect. I would say by this time you would have understood that there was considerable amount of ecosystem already developed, not just in the form of network vendor infrastructure, but also in the form of mobile phones, as well as maturity in terms of the applications that you use on the mobile phones. Okay, let's move on. You might get a little carried away with this, but I would suggest not to do that. Uh, what you can see on the screen right now is an end-to-end network architecture. Let me use a pointer here. What you can see here is an end-to-end network architecture. You might be wondering where is 4G here. I will come to that in a minute. But then before you get overwhelmed with too many network elements mentioned here, it is very important for you to understand at least at the high level aspects, right? I'm not going to talk about these network elements very detail, but then please understand that this is that part of a network which is responsible for providing packet data service to the user, right? Now you might be wondering when somebody said what are the uses of a mobile phone network or a mobile or a cellular network. There are basic two uses at a very high level, right? One is voice and the other is data. So you have both voice and data service provided to the common man. Then why are we talking about a network which is basically able to cater only to the packet data service? Why is that? So the answer to that question lies in the fact that when LTE network initially got developed, the basic requirement to develop 4G network was to provide improved data throughput. But then all the network operators around the world had a strong suggestion or a request towards the ecosystem or the infrastructure providers that please do not waste the investments that are already done in 2G or 3G for us. Ensure that our 2G and 3G network infrastructure can be at least reutilized for voice-based services. We are more or less okay in terms of the capacity. We are more or less okay in terms of the quality, or let's say we are more or less satisfied with the amount of voice quality that we are able to provide to our end consumers. So whatever development that you do, ensure that the first target for that is providing better data throughput. So that's the very reason why initial development was mainly focused on the data network. So when you Google, right, a GSM network or a WCDMA network, one of the key network elements that you might be missing, or let's say more than one, I would say 2 to 3 network elements that you would be missing in this architecture is MSC, MGW, HLR, of course, is already there. So similar network elements that you will be missing in this slide. The reason why they are not here is they provide MSC and MGW. They are critical components to provide voice-based service. And they stay as it is even when LTE network gets initially evolved, because LTE network was initially not meant for providing voice-based service. The same LTE subscriber moves into a 2G or a 3G network to make voice calls. And once that is done, once those voice call services requirements are finished in 2G, 3G network, you can again come back to 4G and use the network for packet data service, or let's say a data service. So let's get started in terms of what these network elements do at a very, very highest level. As you can see in this picture, that there is a network element called as BTS on the left hand side, and there is also something called as BSC, right? So BTS stands for base transceiver station. It is basically used in a GSM network, and it comprises of radio transmitters and receivers. And then of course you see those antennas which are there on top of the buildings, right? When you see a tower, it will always be connected with an antenna, and from those antennas you can actually see some blue color cables hanging or black color cables hanging around. They always go to a room which is there on the tower, and that room consists of a machine kept inside. That machine actually is called as BTS, base transceiver system. So BTS is a critical component of the radio network in GSM, which comprises of radio network BTS transmitters and receivers, their associated antennas, and these antennas transmit and receive directly, or let's say they communicate directly with the mobile phones that you have. So the BTS is a defining network element for each cell. Now, what is this cell? It is not a cell phone that I am talking about here. What I am talking about here is a mobile phone which is able to access a particular network in a particular coverage area. So this coverage area, as depicted here in the form of a hexagonal shape box, this particular coverage area box represents a cell, right? So BTS is actually a defining element for each cell, and for each BTS you will have a particular coverage area which this BTS can transmit or receive based on certain frequencies, based on certain transmission and reception power that the BTS can have, and also your mobile phones can have. So BTS communicates with these mobiles, and the interface between the two is known as interface. So let me actually show how the complete network looks like. Of course, I'm bound to show this LTE network as well. So what you have between mobile phone and 2G network is actually the UM interface. This is the UM interface. So you can imagine there is some sort of a wireless interface between the mobile phone and the BTS, or let's say the coverage area. So that's about the BTS. And talking about BSC, it consists of a group of BTSs. Basically, it can control n number of BTSs. This is what I'm talking about here. And this BSC is actually sometimes, not all the time, for some of the BTSs, this BSC is actually co-located. So what does it do? It manages the radio resources. It controls items such as handovers within the BTSs. So let's imagine when I say BSC controls more than one BTS, you can imagine in a commercial network or a typical on-field network, there will be around 30 to 40 BTSs in a generic way for understanding purposes. Let's say for all these 40 BTSs, BSC will be common. And for all these 40 BTSs, how do you ensure that the mobile phone moves from one coverage area to the other coverage area? How do you ensure that the communication from the mobile network towards the other user is actually not interrupted? That is only possible when you adapt a system, or let's say a concept or a feature in the network that is possible in the form of handover. So what is handover? Handover is that kind of a process in which the call, which is established in a particular coverage area, is transferred from one coverage area to the other, and there is no interruption in the services whatsoever. So when I say services, it can be a voice call based service, or it can be a data packet or packet data service. So when a user is making a voice call, or when a user is making a packet data browsing session, and he is on the move and he moves from one particular coverage area to the other coverage area, then in that case, this concept of handover ensures that there is no interruption to his session. So cellular services basically are they are based on mobility, and concepts like handover. They allow the user to move from one area to the other. That's at the end of the day. That is why you call the user as, or let's say the phone user as mobile phone user. Otherwise, he'll still be called as a landline user, right? So handovers are typically important element, and they're used in planning and deploying these cellular networks. Okay, so 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 we have talked about BTS, we have talked about BSC. These two typically together with the coverage area, they make for the radio part of the network, or radio network across the end-to-end portfolio. So similarly, in when you move from 2G to 3G, you had different air interface technology. It was not called as UM anymore. It was called as the WCDMA based interface, and then the BTS was called as now Node B. Okay, there's not huge difference other than the fact that they just wanted to represent it with a different term. B at the end of the day still stands for BTS. So Node B or BTS is almost similar to the 2G variant, and RNC is still a radio network controller. So it is still a counterpart for BSC in 3G network. One important thing that you might be already or you have already noticed is the kind of interfaces that are there in between, right? What you see here is a solid line, and there is a dotted line as well. So when you move to the right edge of the screen, you can see that dotted line represents control plane, which is basically meant for establishing signaling connections between these network elements, or let's say the boxes that I have represented here in the end-to-end system scenario. So all these dotted lines that you see here are basically meant for communication between these network elements or the entities of a network. These control plane related interfaces, they do not carry the user data or the user voice. The user data or the user voice is rather carried through user plane. So when a mobile phone user is particularly conversing with the other phone user, the voice path will be somehow something. It'll look something like this. It'll from the coverage area, it'll to the BTS to BSC, and then there are certain network elements that I'm going to discuss now. Finally, it'll go. It'll either go to the internet, it'll go to the company intranets, or it can go to certain other IMS services. These are also responsible for voice-based service. So when you are in a LTE network scenario, you would rather not have a CS core network. You can directly have something called as IMS network. So basically, this IMS network represents a perfect counterpart for MGW and MSS in a 2G or a 3G network scenario. So this particular box is responsible for making voice calls. But if you are directly making a browsing session, or if you are have established a browsing session or a streaming or a download or some packet data related session, your path, the solid line, will travel like this, either to the internet or to the other phone user. So dotted line represents control plane, user plane is represented with a solid line. As you can see, you have more or less, of course, the control plane is not represented here. Primarily, this is distinguishing the fact that initially when networks got developed, there was no clear distinction between the control plane and the user plane. So that is why you had this. This can't be purely called as a control plane or a user plane. This is just an interface where both of them are carried together. There is no clear distinction done. But then you can see those differences here. Okay. Okay. We will try to move a little into the core network aspects here. You can see that there is a network box or a network element called as SGSN. You can see that there is something called as SGW or a serving gateway. This is PGW or a packet gateway. And then you had MME. So what is the major difference between a 2G, 3G network and a 4G network? Remember, before we talk about these things, we have already dealt with something called as BTS and BSC or RNC and Node B, and the radio part of the network is already done. Okay, what we are going to talk about is the core network. So when I say core network, it is primarily meant for packet data. The discussion is focused on packet data. So I am talking about packet core network. So SGSN or the serving GPRS support element is a particular component of GPRS network. It is responsible for packet routing and the transfer of all the information that you have from one user to the other. And then it is also responsible for mobility management. So there are a lot of control plane messages exchanged from radio network towards core network, even while you are doing handover. So the decisions with regards to which coverage area you have to move, and when you move to that coverage area, what kind of critical network parameters are required, and whether those conditions in the destination network or a coverage area are sufficient for you to do a handover. All these decisions are made by the controller here as well as the core network here. So that is the mobility management part that it deals with. It might so happen that this SGSN is no more controlling the BSC or RNC that you have in a target or destination coverage area. So this SGSN has to deal with other SGSN as well. So mobility management actually takes care of all these aspects. It also basically takes care of attach and detach. Basically, attach is nothing but the initial camping or initial connection that mobile phone establishes with the network. So attach and detach are already taken care by SGSN. And then you also have critical things like authentication that is responsible for uniquely identifying a subscriber in the network. And also, uh, you initially had these charging concept, right? So of course we still have that concept, but it is dealt in slightly different way. So for a particular session or a packet download session or a voice call that you have, there is certain level of charging that is done by the one of the core network elements here. Even though there is a dedicated element for charging here, critical inputs with regards to how many minutes user has utilized the services of the network, and then what kind of a profile he has. All this information is fetched by SGSN, and it critically acts as one of the coordinating entities for charging to be performed. So charging is also done by SGSN. So SGSN is also important in the context that uh, there is some kind of a location update done. So it critically tracks the location of a particular subscriber. When it comes to the voice core network, or let's say the CS core or the voice component of the network, there is something called as VLR. You might have seen that in GSM network. So VLR is responsible for maintaining temporarily the database of the subscriber, including his latest location. So when it comes to packet core network, SGSN does that. It takes care of ensuring that the temporary location of the subscriber is stored and it is used whenever there is a requirement. So it also stores the profiles, what kind of a subscriber he is, what kind of IP addresses that are assigned to these subscribers, and then for all these users, it tracks the subscriber related information. So how does SGSN do that? SGSN fetches this information during the initial network attach for the mobile phone. Whenever a subscriber tries to access the network, SGSN fetches that information from HLR or HSS, as you would call them nowadays in LTE network. So HSS or HLR is that kind of an entity which is acting like a permanent database for the subscribers uh, whenever they procure services through a SIM card. So for that particular SIM card, there will be subscriber related information, what kind of a IMSI or IMSI. We call it as IMSI. You can properly refer to that as a subscriber information, where what kind of a network access that does he have? Does he have pure voice-based services, or does he also have packet data services? If he has packet data services, how much is he allowed to download per day, per session, and stuff like that? How much data loads or how much downloads can he have, and how much upload speed can he have, and what kind of a prioritization he has? All this information is basically stored in HLR. And whenever you provide access for subscriber to the network, this AAA or accounting and authenticating service is responsible for allowing a user to perform the control plane procedures and further the user plane, or let's say the voice and data services from the network. So AAA is responsible for providing the authentication to the subscriber, and at the end of the day it is still SGSN which does that coordination. So what else? We will touch base upon PCRF when we talk about LTE network in detail. So what you can see here is SGSN. There is something called as SGW and PGW. They are basically a counterpart for something called as GGSN we had earlier. GGSN was a gateway GPRS support node. It was one of the most important entities within the GPRS network. So it organizes the combined entity of these two, organizes the interworking between the GPRS network and external networks that you have. So basically, it is acting like a coordinating entity or an interworking entity, and it can also include the external party can also include internet as well as other X.25 networks, or let's say company intranets. So This combined entity, SGW and PGW as we call it, can be considered to be a combination of a gateway, a router, and firewall, because it hides internal to the network, and it ensures that this hiding of the internal network is done towards the external world. So in operation, when the basic combined entity receives the data addressed to a specific user, it checks if the user is active, it forwards the data. In the opposite direction, packet data from the mobile is actually routed to the right destination by the GGSN. So how does GGSN ensure that the packet which is generated from a mobile phone or a user actually ends up in the right place in the internet? We will talk about that in the coming slides. So that's about the SGSN and the combined entities of SGW and PGW that we have. So let's move on. So what we have here is an E node B, and it establishes a direct connectivity towards SGW. But if you see the yesteryear's network, you have BTS and BSE. The essential part of user plane and control plane actually goes through the SGSN, and you cannot avoid SGSN here when it comes to 2G network. So when it came to 3G, there was a decision taken not to overload the SGSN with all the user plane information. So RNC rather had a direct connectivity towards SGW for the user plane purposes. So it is this evolution what I am talking about. So at the end of the day, when you go from 2G to 4G network, it is not that E node B, of course, is a collection of both node B and the controller. But then when it comes to the network evolution or the interface evolution, it is not that it has directly got designed without any retrospection. So what you had here is user plane and control plane here. It is divided during release 9 architecture, release 99 and release 4 architecture. And then LTE had to reuse that concept to ensure that the counterpart for SGSN, which is MME, is actually not overloaded here as well. So MME is the key control node of the LTE network. It is basically responsible for user equipment paging and tagging procedure, including retransmissions. It is involved actually in the bearer activation or deactivation process. At the end of the day, it is also responsible for serving the right SGW that you have in this network. So we will see what MME does, what are its details. Let's move on with regards to the OSI system that we were talking about initially in the agenda. So the takeaways from this slide are that you have a radio network, you have a core network, you have something called as control plane and user plane, and then you had something called as critical charging and subscription related entities. You also have a box related to IMS network, and this is responsible for providing a voice service to the LTE subscriber. So let's move on. So basically, this is one of the critical evolution. I would say I will not take much time on this, but then this indicates how the Nokia product got developed from 3G to 4G. And when I say evolution, we were basically talking about release 7 to release 8 architecture. So it's okay, we can move on with the other important aspects. So here comes the OSI model, right? So we were saying that all the existing systems that we have today are built on OSI layer models, and it's actually OSI model is developed by ISO. ISO stands for Internal Standards Organization, and this OSI model provides actually a clear distinction between what kind of services that user requires, what kind of services that you can have, what kind of interfaces you have, and what are the underlying protocols that you need to establish before a entity X communicates with an entity Y. So there are so many aspects to it. Of course, if somebody is talking about OSI model and its advantages, it actually reduces the complexity to a greater extent, and in terms of standardizing the interfaces that you have. So it is basically an interoperable technology. You have 7 layers in that. We will go through what they are, and these protocols can be actually when the system evolves from OSI model to new models like the telecom layer model that you have, they can be replaced with new protocols. New protocols can be designed, but the basic idea behind developing these interfaces will still remain the same. The objective behind designing such a modular architecture remains the same. However, I must say that in telecom layer model, what we have is a 5 layer architecture, in contrast to what you have in OSI, where you have 7 layer model. So this model acts as a frame of reference in all communication designs and networking designs. So when products get developed in the field of communications and networking, OSI is actually like a Bible for formulating such new models. So it offers flexibility to adapt various types of protocols. So there are 7 layers here. When you go from top to bottom or bottom to top, this is how a typical layered approach looks like. I will not uh, directly go into the details of this. It's already given in the slides. But then the important aspect here is that the 7 layer model that is depicted here is actually, as I said earlier, used, or let's say reused, in designing the telecom layer model. Okay, but then one must also notice here that this particular OSI model supersedes the TCP/IP model. One might be wondering what are the differences between the OSI model and the TCP/IP model, right? So OSI layer has typically 7 layer architecture, and then TCP/IP has 4. The OSI uses the network layer to define all the routing standards and protocols. But when it comes to TCP/IP, it uses the internet layer. Sorry for that. And the session and presentation layers are actually part of the OSI model. But then when it comes to TCP/IP, there is no session and presentation layer as such. That is one of the key differentiating things when you look at the TCP versus OSI. So OSI actually replaces the TCP/IP model that you have, and it is one of the leading approach that communication uh, network developers have adopted. So physical layer is actually dealing with the transmission of zeros and ones, and then the data link layer actually deals with management of flow of data. When you move from data link layer to network layer, this is primarily meant for addressing and routing the packets. As you can see that the example is, if the packet size is large, it is split into small packets. So this is the responsibility of network layer to ensure that this is cut into several chunks and then reassembled at the other layer, right? At the other end of the system, perhaps at the same network layer. Transport layer is actually ensuring that the end-to-end delivery of a particular packet or a message is arriving at the destination in the right format, and it ensures that it is error free basically, and the message that is to be forwarded from source to destination should not be crippled by the path it chooses, and then the packets that arrive at the destination should be exactly matching those which have originated from the source. So basically, to say that, to give an example, if you say hi, hello, how are you, it should arrive at the same way at the destination as well, right? If all the packets from the source arrive at the destination, and if they still do not arrive in the same order, it doesn't make sense. The destination may not be able to actually comprehend what is arriving at the destination. So that is very important. Session layer, of course, this is meant for establishing, maintaining, and terminating a session. So in a context of LTE network, we call them as bearers. Establishing, maintaining, and terminating such a action is performed by session layer. And presentation, it ensures that the format is in the right way, the protocol conversion is done, encryption is done to ensure security for the user and voice and data, and then the needed graphics are taken care. Of course, application layer is what you see on the mobile phone screen, or those network elements which are maintained in the network. They actually do have some kind of an interface for service purposes. So application layer works in every product. It is basically a user interface which allows you to communicate with the underlying layers that are there in the network, in the system rather. So examples are given here. So we have heard about various technologies in GSM, GPRS, H, WCDMA, HSGPA, DPA, and LTE, right? They are basically the link layer protocols. So in the context of TCP/IP framework, they all get positioned here in GSM, in link layer basically. So the underlying access technologies that you have, frequency domain multiple access, or time division multiple access, WCDMA or OFDMA, this is basically the air interface technology in LTE. They're all part of the physical layer. And then you have networking layer, you have transport layer, and you have the application layer. So it is generalized. The 7-layer model is getting culminated into 5-layer model here. The same picture what you have seen earlier in an end-to-end context is re-represented here. So you can see radio network, you can see the core network, MME, SGW, and PD and gateway, and then you also see HSS, PCRF, and other important functions. We will see what they are. But this slide actually is meant for giving some sort of a reference to the user that these are the technical specifications as part of 3GPP, through which you will understand these functionalities of network elements in a much more comprehensive way. So that's the purpose of this slide. Okay, let's go into the details of eNode B. Not too much, but then just for the sake of making sense of what is being depicted here. Uh, eNode B, as I said, is evolved Node B. It is the only network element which is defined as part of EUTRAN. EUTRAN is actually an evolved EUTRAN. EUTRAN is nothing but a radio network for 3G. EUTRAN is nothing but evolved UTRAN, which represents the 4G radio access network. So wherever you see E in 4G network system, it indicates evolved. So a EUTRAN is an evolved UTRAN, an E node B represents evolved node B. And the packet core, which was there in 2G, 3G, is called as EPC, which is evolved packet core. So this is how you distinguish the 4G network elements. But then the basic functionality, the basic need of such a network element is more or less similar when you compare with 2G, 3G. For example, eNodeB is responsible for radio admission control. It is responsible for measurements, collection and evaluation. There are so many functions that it does. One of the things that I would like to talk about here is the measurements. So what is measurements and why do we require measurements? In the context of uh, in the context of establishing a proper communication with the network, we always say that you need to have a good signal strength with the network, right? And how does that signal strength between your mobile phone and network get established? It is basically between the mobile phone and the network. However, for every there is a setting, kind of a setting in the LTE network by the network, and it is requesting user or the mobile phone to deliver certain signal level measurements periodically. Let's say for every 30 seconds or 1 minute from the mobile phone towards the network, and this ensures that the network or a radio or a core network is able to say that mobile phone in its present coverage area is good enough to have communication sustained for longer periods. And also measurements are very important aspect from the fact that when the user is moving from one coverage area to the other, these periodic measurements ensure that the call or the session is handed over from one coverage area to the other. So they form essential part of the mobile network, and then eNodeB does take care of these measurements. Another thing important here is ciphering and integrity protection. Ciphering is different from integrity protection. Ciphering ensures that the user data or a voice is actually encoded when it is transmitted from the source, and it is deciphered when it is arriving at the destination end. So there is some level of security provided. And the integrity protection ensures that the data which is originating from the source is arriving in the right format without any losses, without any deviation in terms of the critical user information that has arrived at the destination. So integrity protection ensures that the data is arriving in the right format, in the right sequence, and ciphering ensures that the user data is secured to ensure that it is preventing certain uh, eavesdropping or other similar attempts by the hackers. So we have talked about measurements, we have talked about ciphering and integrity protection, and of course, these are the details that you will find most of the uh, generic information. So from the interface perspective, eNodeB has two interfaces. One is control plane interface and the other is the user plane interface. Both of them are represented by S1 MME and S1U respectively. So the control plane interface is that interface which is there between eNodeB and MME. And this interface, for example, takes care of the tracking area update, or let's say when you move from one area to the other, that particular coverage area information is updated using this interface. Remember, this interface is not meant for carrying the user plane information or the user voice and data. It is only meant for signaling exchange between eNodeB and MME. Okay, so S1U as given here, it is basically a user plane interface. It is a pure user data interface where voice and data is carried forward. So while serving gateway, a user's bearer, or let's say the information from the user, will have to use this whichever MME says to use it to. So MME decides which particular serving gateway has to be used during the call. So it is not that you will have a serving gateway permanently assigned to a subscriber throughout its connectivity with the LTE network. It is not like that. Serving gateway has to be decided by MME. There are various, I would say, uh, mechanisms or logics developed in MME to ensure that the right serving gateway is used. You will know more about the serving gateway selection when you read the topic related to initial attach, where serving gateway is selected based on the tracking area or the coverage area related information that MME retrieves from the eNode B. So based on tracking area, serving gateway is decided. But then that's the details of that is not in the scope of this presentation. So uh, the protocols that are there between eNode B and MME are typical control plane protocols. L1, L2, they form together the basic physical layer and data link layer. You also talk about the IP layer, which is a networking, and then you have HTTP on top of that, and then you have application layer protocol, that is S1AP. So again, as I said, you have these technical specification numbers given. You can obviously open them offline and you can read them at length. What is the purpose of all these protocols in detail? So this figure represents what kind of a specification that you can refer to. Moving on with the MME, as I said, MME is a pure signaling entity. Uh, it's a pure signaling entity or a control plane entity inside the core network. So the core network is called as EPC. EPC again, as I said, represents evolved packet core network. So the serving gateway uses tracking areas, which I already said earlier, and MME handles these attaches and detaches to the system. So therefore, it possesses an interface towards the home subscriber server. As I said earlier, in case of 2G, 3G network, you have SGSN, which is responsible for retrieving the unique subscriber related information. The same way, MME also retrieves such subscriber or subscription relevant information from the HSS. And you can see that the interface between MME and HSS is called as S6A. Okay. So what are the typical MME functions? The non-access stratum related security. So non-access stratum is actually that kind of a communication platform that gets established between MME and the UE, or let's say the mobile phone, directly. So when I say directly, it doesn't mean that mobile phone has a direct interface towards MME. It will obviously get established through eNode B, but then eNode B does not process those data related to non-access stratum. It will simply transparently forward it to MME, and MME uses this non-access stratum to perform authentication and integrity protection. How the authentication is done, how the integrity protection is done, is actually not part of this scope, but you can obviously refer to that offline. What are the other functions of this MME? It takes care of idle state mobility management. It takes care of tracking area updates, subscriber attach and detach. It takes care of security control and other functions listed here. So mobility management function, on the other hand, has so many interfaces. It is one of the actually key elements of a core network here. On one hand, you have BTS, that is eNode B interface that we already discussed, which is S1C. The other hand, you have uh, MME having an interface towards HSS, which we just discussed now. It is called as S6A, where it retrieves the subscriber related information. And the same MME also has but very important interface towards the serving gateway that is called as S11, right? So it is interface between MME and the serving gateway. It is used to coordinate the establishment of bearers. So right from the time you switch on the mobile phone and right from the time you switch on the mobile phone and then till the time you get the signal on your phone, or let's say the tower on your phone, MME is responsible for all such sort of internal communication that happens among all these network elements. And this happens
as you might have observed, let's say in a couple of seconds, 2 to 3 seconds, right? So these are the huge number of control plane messages which get exchanged, and MME forms a critical component of these uh, messages, and this is used for establishment of such a bearer. So when I say bearer, this is that sort of a carrier which gets established within the core network. So the bearer setup can be started by MME or by the PDN gateway. So when you are originating from the mobile phone to request for a session, so that is started by MME. When you're receiving from the mobile phone user and you are at the receiving end and that kind of a network, the direction of the control messages will be on the other direction, right? You will be, uh, let's say here, let me go back. When you are at the receiving end, sorry for that, I just need to go back to show you how it works. When you are at the receiving end, the call, the request is received via the other direction, that is P gateway and SK gateway, and then it will come to MME. So when you are making a phone call, or let's say when you are starting a service session from the mobile phone, it originates, but when you are receiving, the direction will be the other way. So in the originating session, MME plays an important part in establishment of carriers, and in the receiving end, PDN gateway forms very important role. So this is what I meant here with this. Let's move on with the next topic, that is serving gateway. You might have actually seen what serving gateway does. For the benefit of time, I would like to emphasize here on one of the typical, one of the important rather functionalities of serving gateway, and that is mobility anchor point. So you can understand from the very word that is mentioned here to describe what sort of a functionality it does. We have mentioned here anchor, right? Anchor is actually that kind of a let's say a device or an object that is used at the seashore for ensuring that your your boat or ship which is connected at the shore doesn't get lost into the sea. It ensures that your boat or ship is actually clinging onto this bank, right? Otherwise, if there is no anchor, your ship or boat will get lost towards the sea. Similarly, when a mobile phone user is getting is connected to the network, till the time he is connected to the network, whatever whatever data it already has, the subscriber has, when he's moving from one area to the other, the existing data session should not get lost, because what you have happening here in the backend is your coverage area is changing from one to the other. So when coverage area changes from one to the other, the E node B also gets changed accordingly. So when E node B also gets changed accordingly, the direct connection that is there between the E node B and the serving gateway, what you call as user plane, will also get changed, because the E node B is getting changed. So when the time, let's say a 0.5 second or a 1 second time interval that is there between a user connected towards one E node B and shifted towards another E node B, during this time interval, whatever session that is there with the user should not get lost, right? Sorry. So whatever session the mobile phone has with the network should not get lost just because you are shifting from one coverage area to the other. So that data is actually buffered inside the serving gateway, and that is why you call it as anchor point. One of the key aspects of this anchor point is this. So the switching the user plane path from one eNode B to the new eNode B in case of handover is actually done by serving gateway. And what are the other functions? Okay, at the end of the day, it is not an independent entity. It is still controlled by MME. When I say controlled, it is decided by MME as to which serving gateway has to be used during the call. Of course, there are certain government agencies or local government agencies which are requesting the mobile phone operators to provide the lawful interception. So you do have this functionality which is there but not used widely unless and until the local administrative authorities request for it. Okay, I would say this PDN gateway, that is Packet Data Network SAE gateway, as one of the gateways to the external world. So that is why it is actually fitting to call it as a SAE gateway. Uh, this is basically comparable to a GGSN as I described earlier. The major functionality provided by PDN gateway is the QoS coordination between the external PDN and EPC. So QoS actually stands for quality of service. So let's talk about QoS for some time. Uh, QoS, as I said, stands for quality of service, and based on the session that a user has with the network, it is imperative for the operator to provide a certain quality of service based on the service that he would like to use. So what kind of service that a typical user has? It can be voice or data. And then within the data, you have several types of usages that you can think of, right? You can think of a browsing session, you can think of a download session, you can think of a streaming session, you can think of online gaming, you can think of video calls, etc., right? At the end of the day, the different requirements or the stringent requirements that certain applications demand from the network are actually not the same compared with the other functions that or services that a user uses. So typically a download session demands you to have higher throughput or higher uplink and downlink throughputs. But then it does not demand you to have a real-time experience with very less delay from the network. That's not a real use case of a throughput. The real use case of a throughput is to provide as much speeds as possible or data rates as possible so that you finish your downlink or download of a file or an upload of a file. But in contrast, when you perform a video call or a voice call, the delay in the network should not be there. It should be as bare minimum as possible, right? So actually, when you think of it in the form of a video call, the throughput requirements will not be of the order of 30-40 Mbps. They may not be even 10 Mbps. They might be at the, around in and around 4 to 10 Mbps, I would say. But then throughput actually is not a critical component for critical requirement for making a video call. What is more important for a video call is to have as much delay, as less delay as possible. So latency, one of the key factors responsible for ensuring that there is no delay is actually achieved through this QoS profile. So that is where QoS profile plays a key role. So video games, video calls, these all let's say even the streaming to a certain extent ensures that they all demand real-time usage or real-time response from the network. So they have a different set of service requirements compared with a typical download or a browsing session, where it is okay to have a delay of 1 or 2 seconds, but then if you have a file of 10 GB or 100 GB, you would like to have it quickly downloaded. So when the download starts is actually not a problem, but then when it starts, it is okay if it can go at a high speed in spite of starting at a 1 or 2 seconds. So that's the requirement of throughput. So QoS is very important aspect of core network, and PCRF is actually responsible for designing those quality of service requirements, and PDN gateway is more or less like an implementer. Okay, so PCRF is like a manager, and you can visualize PDN gateway as an implementer or a or like a enforcing function. So policy enforcement is done by the PDN gateway, and these policies are designed in PCRF. So another important aspect is, as you all well aware, I think nowadays within your labs and other places, you know for the fact that if one in the internet, it's internet is basically a group of machines talking to each other, right? Can I simply call it like that? Internet is a group of machines, but then these machines talk to each other using the IP protocol, that is Internet Protocol. So IP protocol demands you to have an IP address assigned for you to be able to converse with the network. Of course, there are other requirements like gateway to be assigned and gateway to be reachable. You need to have a physical network connectivity, blah, blah, blah. But at the end of the day, what is important for you to take away here is that the device needs to have an IP address assigned. Unless you have an IP address assigned, you cannot communicate with the outside world. Similarly, in the context of a mobile network, when if you can visualize the mobile phone as as a as one of the computers which are there in the internet, the only possibility for you to access the content on the internet or on the other phone is by providing an IP address for the mobile phone as well, right? So mobile phone can talk to entities like BTS. When I said talk, I mean establish communication with the BTS or eNote B, and establish a user plane path towards serving gateway. And let's say if you are trying to access google.com or gmail.com or YouTube or whatever, ultimately you need to have an IP address assigned to yourself for you to be able to talk with a IP address based machine. So that IP address assignment is done by PDN gateway again. Okay, there is a functionality called as let's say there is a parameter called as APN, access point name. I think in the yesteryears you might have already seen in certain feature phones that there is or even now you do have if you go to settings in the network settings, there is something called as access point name, like airtelgprs.com, airtelmmsdata.com or something. This access point name is actually configured inside the PDN gateway. So based on the APN that is assigned for the subscriber, PDN will ensure that that particular access point name is converted into an IP address for the user, and this IP address is unique, and it is based on it is one of the IPs which is there as a subnet for that particular access point. So you have XYZ access points, and for each access point you will have a subnet assigned, and among those subnet of IPs, one particular IP will be picked up and it will be uniquely assigned to a user, and every user will have his or her own IP address assigned by the PDN gateway. So as long as you are connected to the LTE network or a packet data network, this IP address allocation is intact. So that is one of the key aspects of IP address allocation here. Of course, when you talk about serving gateway and PDN gateway, the main difference between S5 and S8 here is S8 is used as an interface in case serving gateway of operator Y is going to talk with PDN gateway of operator Z. So if serving gateway and PDN gateway, they both belong to the same operator, then you have S5. But if both of them belong to a different operator altogether, what you have here is S8. So S8 in a way can be visualized as a S5 network. Certain interoperator security functions are also embedded inside S8. So that's the main difference here. Policy and charging rule function. As I said, one of the critical functionality is to provide quality of service, and it also ensures that It resembles the policy and charging control framework introduced in IMS, and that's one of the reasons why it is still called as charging rule function. It frames the rules basically for charging the subscriber. HSS, as I already said, is a permanent database, and it stores the data of the subscriber, and it also aids in authentication functionality. There are certain keys, certain algorithms, and certain input random number and responses that are exchanged among the network elements and the phone during the authentication function. You can actually Google that. So all these parameters are exchanged by HSS towards the mobile phone to ensure that the mobile phone or the user is uniquely identified and authenticated before he or she accesses the network. So that's one of the functions of HSS. You can always associate this word HSS with a certain release. Prior to UMTS release 5, you had HLR here. And one of the protocols that, I mean, the actual protocol between MME and HSS is diameter, and it is based on interface called as S6A. Okay, so we have arrived at the end of the session, and so remember that one of the key takeaways for you is to understand which is the radio part of the network. This is a particular radio part of the network, and the other part of the network is EPC, that is Evolved Packet Core Network. So please try to remember this at the very highest level, but then as and when you deal with each of them in detail, when you get the opportunity, you can then think about remembering these names. But otherwise, I would strongly recommend for you to first of all make sense of what these functions are at a very, very highest level. And then when you get time and interest, and whenever you have such time, you can obviously refer to these technical specifications. So thanks for your time, and have a nice day.